You are tuned to Iri-e-learning, and I am your host, Teacher. In this structure and bonding lesson, we will examine the properties of ionic compounds. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to describe how ionic compounds form giant ionic lattices, explain the different properties of ionic compounds, describe the giant ionic structure of sodium chloride. Recall from our previous lessons that ionic bonds are also known as electrovalent bonds. Likewise, ionic compounds are also called electrovalent compounds. One of the first misconceptions we need to get rid of regarding ionic compounds is that ionic compounds are just the unit of the cation and the anion being attracted together by electrostatic force of attraction. In fact, the ionic compound is a three-dimensional structure of these ions. So the cations and the anions are bonded together in all directions. And the three-dimensional structure created by the cations and the anions attracting each other is called a giant ionic structure or a giant ionic lattice. If you take a look to the right of the screen, you'll notice the ions. Those are the cations, which are positively charged, and the anions negatively charged, form a regular repeating arrangement. So they are layers of regular repeated arrangement of positive and negative charges, and this forms what is called the ionic lattice, which eventually grows into a three-dimensional structure, which is called the giant ionic structure. Note that within the giant ionic structure, the oppositely charged ions of the lattice are held together in all directions by very strong electrostatic forces of attraction, which we know are the ionic bonds. So that brings us to the properties of ionic compounds. The regular arrangement of ions in the lattice results in the formation of crystalline solids. Therefore, ionic compounds are usually crystalline solids. The crystalline structure of ionic compounds is such that it is hard yet brittle. The ionic crystals are hard due to the strong electrostatic force of attraction, which are the ionic bonds between the regular arrangement of oppositely charged ions within the lattice. So the strong ionic bonds exist in all directions around the ions within the three-dimensional structure. The crystals are brittle because they shatter when they're hit. So if a force is applied to an ionic crystal, what happens is that the layer of ions will shift at the point where the force is applied, and at some point the like charges will align. And as we know, when like charges come together, they repel each other and thereby splitting the lattice. Ionic compounds are typically soluble in water. They dissolve in water to form aqueous solutions. Ionic compounds dissolve in water because water molecules are polar. As shown in the diagram, a water molecule has two hydrogen atoms, represented by the red circles with H for hydrogen, covalently bonded to one oxygen atom, O for oxygen. We will examine covalent bonds in the next lesson. Usually in covalent bonds, the atoms share the electrons. However, the atoms do not share the bond electrons evenly in a water molecule. The oxygen atom is more electronegative than the hydrogen atoms, thus pulling the shared electrons closer to itself and further away from the hydrogen atoms, as we just saw in the illustration. As a result, the oxygen atom develops a partial negative charge denoted by the Greek symbol delta, followed by a negative sign or a minus sign, and the hydrogen atoms are partially positive, and we represent that by delta plus sign. The partial negative charge on the oxygen results because the shared electrons are closer to the oxygen atom, and similarly, the hydrogens develop the partial positive charge because the shared bond electrons are further away from the hydrogen atoms within the bond. Now, sodium chloride is a typical example of an ionic compound, and it consists of a sodium ion bonding ionically with a chloride ion. We will use 1 ionic unit of sodium chloride to illustrate what happens when sodium chloride dissolves in water. When sodium chloride is added to water, the partial negative end of the water molecules surrounds the cations, in this case the positive ion, which is the sodium ion, and the partially positive end of the water surrounds the anions, which is the negative chloride ion. And the ions of the sodium chloride structure are separated as the water molecules surround the individual ions. As the water molecules surround the individual ions in the sodium chloride structure, they pull the ions away from each other and keep them circulating in the solution. And so when this happens, when the ions are circulating in solution, surrounded by the water molecules, we form an aqueous solution. The next property, ionic compounds have very high melting and boiling points. As we learned earlier, ionic bonds are very strong. Consequently, it would require a lot of heat energy to break them. For example, sodium chloride, the sodium ion has a charge of 1 positive and the chloride ion has a charge of 1 negative. It melts at 801 degrees Celsius and boils at a temperature of 1465 degrees Celsius. Note that the melting and boiling temperatures increase when the charges on the ions get larger. For example, magnesium oxide, the charge on the magnesium ion is 2 plus and the charge of the oxide ion is 2 minus. Notice that the melting and boiling temperatures of magnesium oxide is much higher than that of sodium chloride. Magnesium oxide melts at 2852 degrees Celsius and boils at 3600 degrees Celsius. Keep in mind that the greater the charges on the ions in the ionic compound, the greater will be the electrostatic forces or the ionic bonds holding the ions. Therefore, more heat energy would be required to break the strong ionic bonds, hence increasing the melting and boiling points. The final property we will examine for ionic compounds is their ability to conduct an electric current. We will use sodium chloride as the standard example of an ionic compound. Now, ionic compounds do not conduct an electric current in the solid state. This is due to the strong electrostatic forces, those are the ionic bonds, holding the ions together in a fixed position. So the ions are actually unable to move in the solid. If we take a look to the left of the screen, there's a demonstration showing that ionic compounds in the solid state do not conduct an electric current. The series circuit is completed by putting the electrodes in the ionic compound. If the circuit is completed, the LED will light up. The electrodes are placed into the sample of the ionic solid. We are using regular sodium chloride, which is table or cooking salt. Notice that the LED does not light up. This is because no current is being passed through the ionic solid. However, ionic compounds conduct an electric current when molten, that is, when it's in the liquid state, or in the aqueous state, that is, when it's dissolved in water. Now, this is so because the ions are mobile, that is, the ions are moving around, carrying the charges, and of course, this produces an electric current. The video to the left of the screen demonstrates the conduction of an electric current through the aqueous solution of an ionic compound. Here we have some distilled water. The distilled water is added to the solid sodium chloride to form an aqueous solution. Notice that the LED lights up. Therefore, aqueous solutions of ionic compounds conduct an electric current. Unfortunately, due to the lack of the required equipment to melt sodium chloride at 801 degrees Celsius, we are unable to show the conduction of an electric current through a molten ionic compound. Sodium chloride. In this section, we will describe the giant ionic structure of sodium chloride. Sodium chloride is an ionic compound that has a giant ionic structure. To the left of the screen is a diagram illustrating the basic arrangement of the sodium ions and the chloride ions within the giant ionic structure. The ions are arranged such that each sodium ion is surrounded by 6 chloride ions. So we have actually taken out a piece of the giant structure to illustrate that. And here we see this, looking at this sodium, it has 1, 2, 3, 4, 5, 6 chloride ions surrounding the single sodium ion. Also, each chloride ion is surrounded by 6 sodium ions. So looking at that chloride ion that's blinking there, we have 1, 2, 3, 4, 5, 6 sodium ions surrounding the single chloride ion. The ions of the sodium chloride lattice are held together by very strong electrostatic forces of attraction between the positive and the negative ions. The electrostatic forces hold the ions in place, and they are also the ionic bonds. The lines representing the electrostatic forces do not exist, by the way, and so if they are removed, we could represent the giant structure in this fashion. So here we have the three-dimensional structure without the lines representing the ionic bonds. The following are important summary points for our lesson. A giant ionic structure or lattice is the three-dimensional arrangement of ions, cations, and anions in an ionic compound. The ions in the giant ionic structures are held together by strong electrostatic forces called ionic bonds. Giant ionic structures, those are the ionic compounds, form hard, brittle crystalline solids. Ionic compounds form aqueous solutions. Therefore, they dissolve in water. Ionic compounds have high melting and boiling points and conduct electricity when molten or in an aqueous solution. Moving ions carry an electric charge and hence conduct an electric current. The giant ionic structure of sodium chloride consists of 6 sodium ions surrounding 1 chloride ion and 6 chloride ions surrounding 1 sodium ion. It's quiz time. You have 5 seconds to answer each question after it is read aloud. Question 1. Identify the statement that is incorrect about ionic compounds. A. Ionic compounds always conduct electricity. B. Ionic compounds need a lot of energy to break ionic bonds. C. Ionic compounds are usually soluble in water. D. Ionic compounds form giant ionic structures. The answer is A. Ionic compounds always conduct electricity is an incorrect statement because ionic compounds in the solid state do not conduct electricity. They only conduct electricity when molten or in aqueous solution. Question 2. Name the type of bond that holds the ions together within a giant ionic structure. A. Ionic bonds. B. Electrovalent bonds. C. Electrostatic forces. D. All of the above. And the answer, of course, is all of the above because ionic bonds are also known as electrovalent bonds, and of course, these are actually electrostatic forces of attraction between oppositely charged ions. Question 3. Which statement is correct about giant ionic structures? A. They are two-dimensional structures. B. They are usually crystalline solids. C. They're crystals that conduct electricity. D. They have strong metallic bonds that hold the ions together. The answer is B. They are usually crystalline solids. That's the only statement that is correct about giant ionic structures. Question 4. Which ionic compound in the table below would have the highest melting point? We will give the name of the compound followed by its ionic formula unit. A. Magnesium chloride Mg2+, 2Cl-. B. Sodium chloride Na+, Cl-. C. Calcium oxide Ca2+, O2-. D. Lithium oxide 2Li+, O2 minus. The answer is C, calcium oxide, Ca2 plus, O2 minus. And the reason why calcium oxide would have a much higher melting point than the other three ionic compounds listed is that the charges on the ions of calcium and the oxide are much higher than the ions found in the other ionic compounds listed. Question 5. Identify the option that is correct about the electrical conductivity of sodium chloride. Option A states that sodium chloride conducts electricity in the solid state only, and this is because the ions are mobile. Option B, sodium chloride conducts electricity in the solid state and in aqueous solution, and this is because the ions are fixed within the lattice. C, sodium chloride conducts electricity in the aqueous solution only, and this is so because the ions are fixed within the lattice. And D, sodium chloride conducts electricity when molten or in aqueous solution, and this is the case because the ions are mobile. The answer is D, that is sodium chloride conducts electricity when molten or in aqueous solution, and this is the case because the ions are mobile, carrying around the electric charge. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.